Yeah, any questions till now? We looked at this curve x2 square equal to x1 cube. It has a point of singularity at the origin, and we resolved it by changing it to the curve y square equal to x1. The transformation is y equal to x2 over x1. Okay, so we are introducing a third variable, and then you see that clearly the singularity at the origin is gone. Right now the curvature is just right. But of course, we in algebra we don't have any concept of curvature, or we cannot draw these pictures. So we are doing this algebraically, and for that we have to develop more algebra. So we have developed tangent space and rank of that. We want that rank to be 1 in the non-singular case. And for resolution, we have defined these discrete valuation rings. Okay, so resolving a singularity is a blowing up process. So we increase the variable, and we basically we want the ring of germs to be bigger. Okay, and yesterday we showed what we mean by bigger is integrally closed. We actually showed 3 properties. So we want first property is we want the maximal ideal to be principal. Okay, this we take as the definition of DVR. But there are many equivalent properties and even definitions of DVR. Second property is that there should be a valuation on the function field. Okay, so valuation means basically a metric. It's a map that sends every field element to an integer such that it should respect the multiplication and it should respect the addition. The axioms are in orange. So for multiplication it should be additive, V should be additive, and for addition it should be at least the minimum. So V of alpha plus beta should be at least V alpha and V beta. And third property was integral closure. So integrally closed means this thing that if for a monic polynomial you have a root in the field, then you actually have a root in the ring. Okay, in that case you call the ring integrally closed. And then we showed that all 3 properties are equivalent. Okay, so we showed that this for transcendence degree 1 field big K, R is a DVR if and only if there is a valuation on the field, if and only if R is integrally closed. So any questions till now? Okay, so now we will see what are the valuations of field of the affine line. Before that, let's pick a more unusual example, or a more basic example actually, that of rationals. So in this case, so DVR within rationals will be, you are looking for a ring R which is inside rationals and which should have a maximal ideal that is principal, right? So one example is you take a prime and localize integers at the prime, right? So these are not all the fractions, these are those fractions where p doesn't divide the denominator, and this is a DVR. It's a DVR because you can see that the maximal ideal is p times R. So it's a principal unique maximal ideal, and the quotient, the residue field is R over M, which is Fp. Right? What is the valuation that it gives on fractions? So valuation V on a fraction A over B, A and B are integers, is defined to be, yeah, the highest prime power of P that divides A divided by that for B. Right, so this is also called the valuation with respect to P of integer A. So calculate that for integer A and minus. Yeah, so calculate that for the numerator and the denominator, and the difference is what gives you the valuation. Right, so this is something you might have seen, but what it tightly relates to is the DVR. So this gives you infinitely many DVRs and infinitely many valuations on the fractions, on the rational numbers. Are there any other options? What do you think? Is there any other way to define this metric V on rationals? So as an exercise, show that these are the only valuations. Okay, for rational numbers, there are no other valuations possible, so they are tightly related to prime numbers.
There's also the Archimedean.
No, that isn't a valuation.
You repeat discrete.
Yeah, maybe discrete. Yes, you want a map to integers. You want a map to integers, yes. So I should say discrete. That's important. It's a good point.
This is the trivial one. You just map everything to one.
Yeah. So no other discrete valuation. There is this non-discrete one, which sends A by B to the norm of A by B. But this is a real number. So we don't count that. Amongst the discrete ones, the way we have defined, yeah, you can show that they all come from prime numbers.
Second one is called Archimedean.
Yeah, that is what he said. But in this course, we have defined it to be discrete valuation, so that doesn't exist. And what we now want to do is we want to look at Kx, right? So let's say you have this field of rationals and you introduce a new variable x. In that case, what are the valuations that you get? We want to study that question. And after that, of course, we will repeat that argument. We'll invoke that argument for the case of curves. Okay, for the case of curves, it will be similar. All the valuations will actually come from the type that we'll describe here. Yeah, so the primes in the ring Kx, the polynomial ring Kx, right? The primes are, every ideal is a principal ideal. So primes will be irreducible polynomials, right? That will be your first guess. So let's define that as a ring. So for an irreducible F, in the polynomial ring, define a subring of K we will call it RF. It's basically like the case of primes. We will look at fractional functions where the denominator is not divisible by f. Everything else you can use in the denominator. Okay, which is the same thing as does it reduce to localization? Probably. Yeah, I think you are just localizing by the prime ideal f. Is the same thing. Yeah, so we'll call this R sub f. We are redefining localization basically, and we'll prove that these are essentially the DVRs for the function field, transcendence degree 1 function field. So the discrete valuation rings of K are this RF for irreducible f in Kx and one more. So you get one more over on top of what you had in the case of fractions. Can you guess what? So it has to involve x, right? Because now you have a new element x. So f equal to x already appears in this example, but there is another thing you can do. You can look at 1 over x. So you can look at R x inverse. Viewing x inverse as an irreducible in this ring. Okay, in the ring, in again the polynomial ring, but instead of x you are using x inverse. So R sub x appears in the first type and R sub x minus R sub 1 over x appears in the second type. Okay, but this is new. It's a different DVR than the above. Okay, you can ask here, why can't we use 1 over x minus 1? Right, if instead of the valuation with respect to x inverse, can we do this for any f, invert it, right, which is I mean the valuation seems to be defined, but will it work? Suppose this gives a valuation V on Kx, then what you can look at is V of 1, right. So 1 is or maybe no, not this, I think okay, let's do this. which implies that 0 has to be at least v of x and v of x minus 1. Is that giving a contradiction?
The valuation of 0 is defined to be infinite or 0? Infinite.
Infinite.
The contradiction will be that here it will be 0. Because somehow v of this x minus 1 is measuring I think the order of the 0 at x equals 1. But then the constant polynomial 0 doesn't have any 0.
Say that again. What is the proof?
So this valuation with 1 over x minus 1
Yes.
is kind of measuring the order of the 0 or pole at 1.
Mm-hmm.
But then the constant polynomial 0 has no 0 or pole at the point 1.
Mm-hmm. At the point 1 it has a 0.
Ah, yes, that's right. At the point 1 it has a 0. Which means it has some non-trivial value, right?
Mm-hmm. So you want to look at valuation of
But
0.
that's not- No, if I substitute 0 in 1 over x minus 1, then I'm not getting 0, right? It doesn't have a 0, right? Oh, but you got v of 1 equals 0.
Yeah.
That should be a contradiction, right? Units can't have 0.
Units are 0.
Units are 0.
Yeah, units are of course 0, which means so valuation of x minus 1 should be 0.
Valuation 1 by x minus 1 is 1.
Yeah, no, but why can't you do the same thing with x inverse? Yeah, I thought I had a simple contradiction, but we have to think about this. Let me leave this for now. But this is getting weird. So valuation of 1 has to be 0, which means this has to be 0, which is a contradiction. But why is this thing not? Why can't we do the same thing with 1 over x?
When you say 1 by x minus 1 is the x minus, you're doing k of x minus 1 inverse, like k x minus 1 is just a symbol. Are you saying?
No, the big field is the function field. So clearly x minus 1 is there and reciprocal is also there.
So it just what's the low DVR here? K of x minus inverse
Oh, the DVR is this.
of 1 by x minus 1.
Yeah, that you can reduce. You will
X minus 1 just becomes a symbol.
x inverse here. It becomes a symbol. No, I mean it is also an element in the function field. So it is that symbol. It's not a new symbol.
But what is the valuation on R sub x inverse for any f?
So valuation is always given by the uniformizer. In this case, the uniformizer is 1 over x. So okay, let's check that.
Largest power of 1 over x.
Yeah, let's check that. So valuation of x inverse will be 1 and valuation of x will be minus 1 then, right? Because you can write x as 1 over x inverse and that gives you minus 1.
Then they are distinct. Maybe you can show that.
No, I think I am.
They are isomorphic. Maybe.
But how can x inverse?
No. I think I have messed it up. No. This is the axiom I am using wrong. Wait. So this is 1 over x minus 1 times x minus 1. On the product it is additive. So what you will get is actually sum. And valuation here was with respect to 1 over x minus 1. So this is equal to 1 plus, yeah, something we don't know. But anyways,
We have x minus 1 and minus 1 only.
this is minus 1, yeah, that is true. Okay, this will not give a contradiction. Yeah, fine. So for contradiction we have to use something else. This won't give a contradiction for x 1 over x minus 1 or for anything. This is just a example calculation. That is fine. Okay, so then I go to a different calculation. I use the axiom on sum. I think that was my original plan. So consider Vx, which is equal to x minus 1 plus 1, which then has to be at least V of 1, which is 0. Okay, that also is not very good. V of x I know is 0, and V of x minus 1 I know is, what else can we try?
The valuation of x minus 1 is minus 1, right?
Yes.
So when you expand that valuation of x minus 1 plus 1, you will get minimum of valuation of x minus 1 or valuation of 1.
No, yeah, which is true. 0 is at least minus 1 or 0. That's not a contradiction. So that is fine. Yeah, I hope that here it will be enough. Some contradiction will come, but it's not happening.
But V of x equals 0 implies x is a unit, which it's not.
No. This is the 1 over x minus 1 valuation we are trying. We are trying to get a contradiction there.
On which ring?
No, there is no ring. We work with the function field, right? Any element in the function field, valuation should work. No, I just wanted to check why is 1 over x minus 1 not falling in these types. So 1 over x, what you can do with 1 over x, you can also do with 1 over x minus 1. I think maybe this is the part which we should look at. Maybe this is the contradiction. So valuation of x minus 1 will be minus 1, and valuation of 1 of course will be 0. So these two valuations are different, right? So when you add x minus 1 and 1, actually the valuation should come out to be minus 1, shouldn't it?
Yeah, it should be the minimum of the two sums.
Yeah, when these two are, when the valuations of the summands are different, then you should have an equality. So actually this should come out to be minus 1. That's the contradiction.
How did we pick it?
Well, this is because the way we define valuation, once we have picked a generator of the maximal ideal, we define it by the divisibility, right? So
Contradiction in the actual definition value.
sorry.
It does not give contradiction in actual definition.
No. So think about it like this. If you have f to the e dividing, if you have a multiple of f to the e and you have a multiple of f to the e plus 1, and u and v are not, they are co-prime to f. So the valuation always picks the minimum, right? Because you can take out f to the e so this property actually tells you that valuation of a plus b actually is minimum if the valuations were different. So this property you have to show first. We haven't shown it before, but we are showing it now, that actually valuation of sum is equal to the minimum as long as the two summands are different valuations.
This is like a strong triangle inequality.
Yeah. So now this is being contradicted above. Okay, you have -1 and 0. So you will pick -1, but LHS is 0. So yeah, that needed more proof. So thus 1 over x minus 1 can't define a valuation. Okay, so there is a significant difference between 1 over f and this 1 over x. 1 over x is somehow very special. Is that clear?
How did we say the relation of x is 0?
Well, 1 over x minus 1, I mean, as you said, x equal to 1 isn't a pole, isn't a 0. Or you just have to see, is x minus 1 dividing it? Or is 1 over x minus 1 dividing it? And that isn't. I mean, at x equal to, so mod x minus 1, it is just 1. So you see that it's a unit there. Units have valuation 0. Yeah, okay. So I think you are now ready to see the proof.
The key property there was basically that there is always some f that you can write every valuation of the form f raised to e is equal to u that time, right? That's why this happened. You always had a valuation in that form. If there is some element f such that f raised to e.
Yeah.
That's the main idea.
That is the, yeah, so this, you have to pick the uniformizer of the unique maximal ideal. Yeah, so because of that, you get this property that we have shown. Valuation is equal to minimum. So it isn't a lower bound, it's actually exactly equal unless the valuations of A and B are different. Then what happens is they cancel out and you can get something bigger, but not here. Any questions? Okay, so yeah, so we have to prove this. Proof is similar to the prime case. So f respectively x inverse can be used to define a valuation. So basically RF and Rx inverse, they are DVRs. So this, how to define it, this you check. I mean, you have to be a bit careful with x inverse because as we saw, bad things can happen. Like 1 over x minus 1, this bad thing happens, but that will not happen with 1 over x. So with 1 over x, the usual thing, check the multiplicity of x will give you a genuine valuation. For rational functions in x. And we have to now show that there is nothing else. So let's show that. So let R be some other of K or in K, it's contained in K, with maximal ideal M and valuation V. So, we will divide into two cases. There is this distinguished element X, either it is in R or not in R. So, let us look at the case when X is in this valuation ring R. So, since X is in R, the whole polynomial ring is in R, generated by X, because K is in R, X is in R, so the whole thing is in R. So, we can actually look at the intersection of the maximal ideal with this, the univariate polynomial ring. The claim is that this is non-zero. Okay, it has a non-zero element. Why is that? So, maximal ideal in terms of valuation represents the positive values. If this was empty, then it means that there is no positive value. So, what will happen? Let us prove this. If the intersection is 0, then every element in Kx is invertible. So, it is in which means I mean, it's a unit, everything here is a unit, so it's outside M, but it's inside R, which will mean, I think it means that the valuation is 0, the 0 map. Is that clear? Yeah, because we are in the function field of this one variable x, and if you are saying that every polynomial is a unit, so valuation is essentially 0. So, just by the non-degeneracy, you know that there is some element here so this is then an ideal of Kx okay. So, this basically reduces to the prime case which we did for integers. So, it is a non-zero prime ideal, and Kx obviously has only principal ideals. So, what you get is that this ideal is generated by a irreducible polynomial. Okay, which means that M itself is generated by this F. And yeah, so you have identified the uniformizer, and that is type 1. So, we are done. Okay, let's go to case 2.
And how did we go from there? Like M intersection Kx is generated by M, that means M is generated by F in R.
Yes. Oh, how did we go there? No, but F is an element in Kx, right? So it transfers to M. I mean, all you wanted was some polynomial inside M.
And so F of R is subset of M. That will imply F generated FO the which is a subset of M. That will
No, if you find an element common to M and Kx, then you have found the generator. So the what is changing is here it is Kx, and that changes here to R. But the generator is the same. Oh no, also you are assuming the fact that M anyways was principal. Obviously from this you cannot show that M is principal. That was given to you. So already M was like generated by U, and you have shown that U intersection Kx is F. From there you deduce.
I think because of irreducibility, if it's not, it has to be generated by some factor.
Yeah.
Does not exist.
Yeah, so something strong was known about M. We are not doing it in general. And case 2. So here X is not in R. So we have again assumed that R is a DVR, right? So if X, the field element, is not in R, then its inverse will be in R. So you use the previous case. We get some polynomial which is irreducible, generating the maximal ideal, and the only thing which will be different, which is not covered in case 1, will be X inverse. Okay, any polynomial, if you substitute there X inverse, then the new thing that you have is actually 1 over X. All the other examples are covered in case 1. So this is the only new one. So that characterizes. Is that fine? Yeah, so we have shown, we have classified the DVRs, the valuations on the univariate function field. From here now, when you want to go to curves,
Once when you go in that case to prove, like we prove that M is generated by F of X inverse, or then,
for some irreducible F.
then you said new R is R of X.
Yeah, so say F was X minus 1.
Okay, we showed that earlier that can't be possible.
So no. So this is X inverse minus 1. So you simplify it, so it becomes X minus 1 over X. But yeah, the X minus 1 part cannot give you anything. It's only the 1 over X,
By 1 by X only.
only 1 by X. Yeah.
You have to prove that X minus 1 belongs to R.
X minus 1, no, X minus 1 will be a unit. Well, okay, so you have to look at that case. Yeah, how to remove x minus 1 and reduce to x inverse. I think you can show that x minus 1 in this case will be a it will be a unit, right? You can show that. So the only new thing you will get is this.
No, if x minus x inverse is in R,
Mm-hmm.
then x is in the field, it is not in R.
Sorry, if so we are looking at, let's say, x inverse minus 1. So this is x minus 1 x inverse, and we are looking at this ideal. Now what?
No, x inverse is not in R.
Mm-hmm.
So x inverse in R, so x is not in R, but you are claiming that x minus 1 is a unit in R.
X minus 1 should be a unit, no?
Why is that happening? If x is not in R, then x has to have a negative valuation. Now, when you are doing x minus 1,
Mm-hmm.
You are getting valuation 0. So, how is that happening? So,
X is not in R, so x has a negative valuation, yes.
yes. So, what will be the valuation of x minus 1? X minus 1 you are claiming that
Pause
x is
it.
0. So, it has to be 0. So, now
No, okay, so then f itself I think gets classified because of that. This can't happen because x inverse minus 1 is a unit, right? Because x was negative, x inverse is positive. Yeah, so since x inverse has positive valuation and 1 has 0 valuation, you again know that this object has 0 valuation.
so x inverse minus 1 is there.
Yeah, so actually what you deduce is that f has to be 0. I mean f has to be x.
Okay, here we are using that the valuation of x minus 1 is negative.
Correct.
Valuation of x inverse is 0. So again that lemma, that negative case comes and
Yeah, that lemma is needed. Yeah,
0.
yeah, that detail is needed. Yeah, I think now it's integrated with this case well, because in any other case other than fx equal to x, you will get the problem of this maximal ideal actually generating everything when this is actually a proper maximal ideal. So you want to ensure that. Okay. Yeah, so once we have done this, we want to now extend it to curves. So we want to do extension of valuation rings. To the function field of curves. So any field k of transcendence degree 1 which is coming from curve, right, can be written as base field small k and transcendence degree 1 field containing this element x such that this is a finite algebraic. And this is the transcendental extension. So for the pure transcendental extension, we have already classified the valuations, which means what we have classified is all these rings contained in small kx in the function field that are integrally closed. Okay, so we have classified all the integral closures we want to extend those integral closures now to big K. Okay, and we'll see that that extends quite naturally. And what we will prove is this theorem, that if R is a local domain in K, and MR be its unique maximal ideal, then there is a DVRB in K with the unique max ideal MB so I want to extend R, right? So I should write R contained in B, maybe here, so such that two things will happen. R is contained in B and MR is contained in MB. Yeah, so basically the DVR that we got for small kx, that is what we are calling R here, and any such R we can extend it to B, which is a DVR for big K, and it will be extending R in both for the ring and for the unique maximal ideal. So this is this condition is also called domination. So we say that B dominates R. Okay, so when I say a DVR dominates another DVR, what is meant is that a local domain B dominates another local domain R when the unique maximal ideal and the ring satisfies this containment property. So you can compare two local domains by this domination relation.
This theorem, like, when is R is a proper subset of B? That kind of
No, R could have been, I mean, R can also be B. We have just said that R and B are local domains, and we have defined domination, and now we are saying that in fact B is DVR.
then we can always make B equal to R and this theorem will be true. That's what I'm saying.
No, R you are assuming to be.
No, R is in the input. R is in the input. You cannot choose it. Whatever R somebody gives you, you can convert it into a bigger local domain, which is a DVR.
Remember, this theorem is saying that there is just some DVR such that R is subset of B, but
Yes.
through this I can just always take B equal to R.
No, but R is not a DVR.
R is not a DVR. Okay.
It's just a local domain.
Okay.
See, because it was a DVR for Kx, it's not a DVR for big K. In our application, that is what you have to remember, that example R is DVR in Kx, but not DVR in the function field of the curve. It isn't a DVR. So how to find a DVR then? So this is basically this is exactly the case of singular points. When a point is singular, its germs is a non-DVR. So from that non-DVR, how do you smoothen it out? So what this theorem is saying, that there will always be an integral. Basically, you take the integral closure.
So we're basically just extending our valuation. We have the valuation that we have and extend that.
Exactly. So you will also extend the valuation. Yeah. Yes, all these things, I think you can think of the proof just as finding an integral closure. There are several ways this is proved.
That, every local domain sits inside a DVR.
Obviously, yeah. The theorem is saying that. And I am giving you the proof. The proof is just in one line. You find the integral closure. That's all. That is just a one line proof. So if R is integrally closed in K, then you know that it's already, then R is already DVR. So you are done. The only interesting case is when R is not integrally closed. So it's not integrally closed means that there are these, some monic polynomials are there with roots in the big field but not in the ring. So you just keep adding those roots, keep growing your field.
Every integral domain sits inside a integrally closed. That is the
Not integral, yeah, then consider a local domain B containing R such that that is an integral closure of R. So I don't need to say this containment. Yeah, just keep adding these points which are missing in R. So ultimately you will get very close to big K and you will have an integral closure of the ring. Yeah, so there may be infinity issues. Why will this thing converge and so on? Why will you stop at some integral closure? So formally what you do is, formally you just define this set F, which is local domain R prime, collect all of them, local domain R prime dominating R, such that 1 is not in the maximal ideal of R prime. So essentially R prime should have a non-trivial unique maximal ideal. So collect all such R primes, right? This is the set. It's dominating, so it also contains MR. So just define this set and say that pick a maximal element in the set. Let R star be a maximal element in F, maximal with the relation of domination, right? So take the maximal element, that maximal element has to be integrally closed, otherwise you will get a bigger one. So formally you prove it like this.
But how do you know that F is not phi, that is not empty?
Sorry?
How do you show that this collection is not empty?
Oh no, it already has R.
But R is not, okay.
Yeah, it already has R, good point. Yeah. So it already has a local domain which dominates itself, and MR was non-trivial, and from that you just collect everything and then take a maximal element, and that will be integrally closed. So that algorithmic proof you can just do it formally with the set, and that's your B, right? So the maximal element, this gives you the formal construction of B, but it's also an algorithm. You can think of this as growing the integral, growing by the integral elements. So that's all It was just this in the proof. You just have to interpret properly. So this is a DVR then. By the proposition, this implies that B is a DVR. That extends R. Yeah, so the proof is simply whatever local domain you have, you keep dominating it by bigger local domains, and you take the maximal one. That's integrally closed, it's a DVR and everything. So some people actually use this also as a definition of DVR. It's the maximal dominating local domain. But we have started with a different definition. These things are all equivalent. Maximal dominating, integral closure, valuation, DVR, all these four things are equivalent. So you have seen all the proofs now. Okay. Yeah, so again the same old example you can interpret. The case of this curve. And R is the germs at 0. So problem was that this R is not DVR. In its function field, and that was because it was not integrally closed, and the example was this x2 over x1. This function x2 over x1 is not in R. Yeah, so this function y was not in R, although you had this integral equation y square equal to x1, right? So you have to introduce this. So when you introduce y, you get 2 DVR. To get B, which is just AY, which is a DVR. In the function field. Okay, so this was the trick we had done in those two diagrams. But algebraically, the motivation is now here. In terms of DVR, it's very clear, and clearer is in terms of integral closure. Okay, you just need to introduce these integral roots, which is DVR in Kx that extends R. Okay, so in this case, as I have said many times, in this curve there was only one point of singularity, and we have resolved it. So now we have a birational curve that is non-singular, right? Now our ambition is to do this in all the cases. So even if you have 100 singular points, you want to do this, and so the idea will be quite algorithmic. You just keep repeating this trick, so that the first singular point gets resolved, and the second one gets resolved, and third one, and so on. Of course, what you have to take care of is that there are no conflicts. So when you resolve the first one and the second one, resolving the third one, you should not introduce any new singular points, or you should not make the first one singular. So you have to do this systematically. So that will be our next goal, how to repeat this. to resolve many singular points. So one helpful condition here is that a curve has how many singular points? Can it be infinite? A curve was a dimension 1 object. Singular points give you this constraint. So if you intersect the curve with another constraint, you get dimension 0. Right? So intuitively you can see that there will only be finitely many singular points.
By constraints you mean?
Yes, so what is this constraint that gives you singular point? So for that you have to go to the comparison results we had. We call comparing tangent space with the rank of the partial derivative matrix, right? So that the first order derivative matrix of the generators of your curve, that is the constraint. The determinant of that, I mean the rank of that should be how much should be
Addition of the
should not be full basically. So that matrix of derivatives should not be a full rank matrix. So you can write that down as a set of determinants vanishing. Okay, so that is an extra constraint which intersected with the curve gives you 0 dimension. So using that you can show it's not very difficult that singular points, they actually form a closed set in your curve, and these points are finitely many. It's a closed set.
So now you will work on the generator of the ideal of those closed set, of that closed set.
No, we will not work with that. No, this is just a statement. We are just saying that singular points are on a curve, they are only finitely many. So we have handled the case of one singular point. We just have to increase 1 to, let's say, 100. It's not finitely many, so it will still be a finite process. So you want to remove the singular points one by one. If we give this, if we give this a kind of inductive algorithm, then you are done because it's a finite algorithm. It will converge. Yeah, so we have to do this a bit systematically, which will need some more geometric concepts. So let us start that.
So this machinery was introduced by Weil, right?
Most probably. Yeah, he must have needed if you want to show Riemann hypothesis for all the curves, then you have to show that somehow very bad curves also relate to good curves, which is this non-singular curves. Yeah, otherwise those curves you won't be able to study. If you cannot remove singularity, then you cannot come to non-singular curves. So it is, for the Riemann hypothesis and other things, it's needed that you have a good curve, which is the non-singular curve where tangent spaces have all the information. Information is not lost at every point. Okay. Yeah, so the systematic way to do this is the following. Consider any transcendence degree 1 field K we want to think of it as a curve, which we'll call an abstract curve. Via valuations. So the idea is that we got to valuation because we were looking at a point on a curve. The point defines the uniformizer, and the uniformizer defines the valuation in the DVR or for the DVR, right? So let's reverse that and make it more abstract. So you can take any function in any field, transcendence degree 1 is important. Look at all the valuations of it and think of the valuations as points and the field as a curve. So how do you do this formally? So formally, let Ck, as promised, let this be the set of all valuations. Valuation V on K with respect to DVR RV and unique maximal ideal MV. Okay, so think of the points on the curve as these valuations, all of them. So what should be closed points, closed sets? So we have the potential points. So once you have points, you have to consider closed sets and open sets to give a topological structure to this, make it geometric. So closed set should be, see, in the case of curve, remember that closed sets were finite, right, on the curve, because a closed set is a zero of some ideal. So if you have another constraint beyond the curve, then you get only finitely many points. So closed sets we should define as finite subsets of Ck. Be defined as those subsets of Ck that are finite or Ck itself. Right, Ck is also a closed set, of course, and everything else only pick finite ones. Right, so that will be a good choice from our experience of curves. Open set will then be complement. Okay, and so once you have points, closed sets, open sets, what remains? What remains is what are the functions on top of this? On an open patch, what are the regular functions, right, which we took many classes to define for curves. So with that experience, now we can say that for an open U, define the regular functions ring as OU, the thing we defined for curves also, So this O applied on an open patch should be what? So remember U has valuations. So you have to define a function which is evaluated on a valuation, right? So this becomes crazily abstract. It's not an actual point. So this should be actually intersection of the rings, the DVRs. So what is the intuition for this? Basically pick an element F in RV, in the DVR RV. How can you evaluate it on V? Right? What is the interpretation that an F in RV is evaluated on V? So you want a base field result. So what you should do is that you should think of that F modulo MV. So F modulo MV will be in the residue field, which is small k. Okay, this is the insight. You think of these elements as functions on the curve, because at a valuation you can just go mod that max ideal, and so it becomes a constant. So hence this is a genuine function definition on an open patch.
So you are saying that that is how we should evaluate.
That is how you should interpret these as being functions. Yeah, a function f, I mean an element f here is, when you want to evaluate it on V, you want to map it to a field element. What will that field element be? F mod MV. F mod MV is a field element. So you are kind of looking at the constant part of the function or the element. We'll develop this on Tuesday. This will need one more lecture to prove the theorem.